Here is the second part of the lecture on thermodynamics. We start with the second law of thermodynamics, and this is what the heat engines are built on. Now, according to the second law of thermodynamics, heat cannot spontaneously flow from a cold object to a hot object, which means if you put a hot object and a cold object in contact with each other, heat is going to flow from the hot to the cold object spontaneously or naturally. If you want to transfer heat from a cold object to a hot object, we have to do work. So here is the Carnot's engine. That's the source at temperature TH, from which QH joules is absorbed, and then work is done. You see the arrow to the right means work is done by the working substance, and the remaining heat, which is QC, is rejected to the sink at TC. All that is clear. That's what we talked about. But then when you look at the pressure volume diagram, you should understand that this ideal gas is contained in a cylinder fitted with a piston. So you have a cylinder like that fitted with a smooth frictionless piston, and that's where you have the ideal gas. So looking at this diagram, can you tell me something about the volume of this gas? Use the words low or high. Low pressure. That's why when you look at the graph, the starting point is M. Because that point shows high pressure and low volume. Are you with me? But then the first process, this is a four-stroke engine. I'm sure you've heard of four-stroke engines, haven't you? It's a four-stroke engine because there are four parts in its working. In the first part, look at this diagram and tell me what it is. The working substance is absorbing QH joules. You can see that. Is this an expansion or a compression? Surely an expansion, because the volume is increasing and the pressure is decreasing. So that is actually an isothermal expansion. That takes place at constant temperature. So Mn is isothermal expansion. Can somebody tell me what temperature that's taking place at?
20 degrees Celsius.
At TH. At TH. Because where is the working substance now? Actually, what you did is you have this kept on the source, just to give you an idea of what's going on. The cylinder is kept on a hot source. Isn't heat going to flow in? That's your QH. And on their temperature is going to be the same because that's very good contact here. That's an isothermal expansion. Look at an NO, which is the second process. NO. Tell me this. Mn or NO? Which one has a higher slope? Surely you remember that an adiabatic has a bigger slope than an isothermal, do you? So, is this an expansion or a compression? Still an expansion, but it's an adiabatic expansion. So, Mn is isothermal expansion, NO is adiabatic expansion, right? So you should be able to tell me what's happening here. So now, the first process, the piston went up, maybe till here, that's the point N. And then at the end of the adiabatic expansion, it's reached O. You see that? And then you're going to bring it back down. You're going to bring it back down. So is it an expansion or a compression now? Compression. So you come back down to, do they call it P? Yeah. You bring it back to P, the pressure increases, the volume decreases. That's an isothermal compression, and then you bring it all the way back to M, which is an adiabatic compression. So there are two isothermals. All right, go ahead. Tell me which are the two isothermals, Mn and OP. Which are the two adiabatics? NO and PM. This is called Carnot's cycle. Does anybody know how to find the work done in this Carnot cycle? We've talked about it. Yes, go ahead. Yeah, take the area of that graph. Take the area inside. That gives you. So you should be writing all this down. No, not just watching And the area of Carnot cycle gives you the work done. The area of Carnot cycle gives you work done. Because these are the important concepts there. So in a real engine, I'm going to speak a little bit about a real engine. In a real engine, would you be trying to make the area as big as possible or as small as possible? What a silly question. Anybody answer? No? Do you want it to do more work or less work? More work. So now if you want this area to be bigger, of course you want the initial expansion to be as big as possible, don't you? You want n to go till here. And then the next compression and expansion to be bigger. You know what I'm trying to do? And then bring it back all the way back. And then back. So you want the area to be as big as possible, which means the size of the cylinder must be as big as possible. That's why when we talk about engines, we talk about, oh, mine is a 3.5 liter engine. Now you understand. Are you getting it? Are you getting some reality connected to this? So I used to drive a motorbike, funny, which had an engine of size 100 centimeter cube. You know how small that is? 100 centimeter cube. An ordinary water bottle is 250 centimeter cube, right? A small water bottle. So having a cylinder which is 2.5 times less than that is like tiny. And that would take me miles and miles when the piston goes in and out continuously. And of course, you don't want your motorbike or car to be oscillating at the same place on the road. So you have to find a way of changing the oscillation into rotation. That's done using a crankshaft. Have you heard of that? Where the oscillation gets converted into a rotation. That's our car. I'm not saying that you can build a car with this knowledge, but that's the basic idea. And I'll give you more as we continue. But is this all making sense? This is where it all started. Here what I've tried to do is just to show you the isothermal and the adiabatic expansion and the compression, as you can see. This is just symbolic, saying you keep a weight there, it'll move it down, so on. But this is the first isothermal expansion. See that? Volume increasing, pressure decreasing. This is the adiabatic expansion. But do you notice something here? What is that? The system is now completely insulated from its surroundings, which means no heat can go out, neither can heat come in. You watch that? And then, okay, that's the source. This is the sink, red for hot and blue for cold, of course. And that's again a compression, isothermal compression, and again it's insulated, which means it's adiabatic again. All right. So I try to explain in every way possible. That's the Carnot cycle that we just discussed. Let's go to a refrigerator. What's a refrigerator? It is a cooling system, of course. It's a heat engine working in the reverse order, in the reverse cycle. Take a look at this graph. What do you see? Do you see the arrows now? Where is heat absorbed from? I mean, from the hot or the cold? Look at the arrow. From the cold, right? So QC, it's the exact same symbols. QC is the quantity of heat absorbed at temperature TC. But then, can you reject heat to a hot object without doing work? Can you? You cannot. So you see the arrow for work now inwards. What does that mean? That means you're having to put work into the system to take the heat from the cold to the hot. That's what it means. And really, I do not like what it's saying here. Please don't write that. Just write refrigerator. Because a heat pump is slightly different. We'll talk about that. So this is a refrigerator. All right. I'm going to give you a good chance now. How do you define efficiency of a refrigerator? there, but this is the actual refrigerator. I wanted to talk about reality too. This is the actual refrigerator that you see at home. How does that work? The theory will be in one place, you know. How does that work? There is a refrigerant used there. The refrigerant is Freon. Have you heard of Freon? Why Freon? The substance used in a refrigerator should have two very important qualities. Or qualities, rather. Let me get you to that. If you take a drop of alcohol or a few drops and put it into your hand, you feel... Why? Why do you feel cold? Why does it need heat? To evaporate. Any substance to change from liquid to gas, it needs its latent heat. You remember latent heat? And it'll take the latent heat from whatever it's in contact with. And what if the latent heat is really high? Would it produce more cooling or less cooling? What if you have a substance on your hand that has a very high latent heat? So isn't it going to absorb the big quantity of heat from your hand, so you will feel more cold? Freon has a very high latent heat. Very important. Unless I say write it, you won't write it. It's like you don't know how to take notes. Freon has a very high latent heat. That's one quality of a refrigerant. Very high latent heat. Did you understand that? What should be the second quality? Let's get to that quickly. Don't keep looking at the diagram, just keep listening to me. So, Freon, which is a liquid, is going to become gas. And it's going to take its heat from the food. Agreed? Because the tubes through which it passes is over the freezer. You're with me? So it's getting that. All right, now it's a gas. Don't you have to convert it back into a liquid so that you can take it through the process again? So how do you change a gas into a liquid? Now, Freon gas, how do you change it into a liquid? You apply a very high pressure. If you pressurize vapor, you know it'll condense. That's what the compressor in a refrigerator does. That's why it needs electricity. So it's continuously compressing that vapor. It quickly becomes what? A liquid. And then you make it go through the process again. And this happens several times in a minute. And very soon you have it cooled. So you see the compressor there, the compressor pump. You see the high pressure vapor. It's the vapor here, but then inside it becomes, they called it low pressure vapor, which could also be a liquid, you know, low pressure vapor. So high pressure became low pressure on one side. So, what did I do? So you have high pressure on one side and a low pressure on the other side. You need a mechanism that separates them. You need a valve. I'm just trying to give a little bit more details. And so that's all you need to build a refrigerator. That's what happens there. You also see an expansion valve. What is that for? That's what I talked about now. You need a valve where it needs to escape from the low pressure region into a high pressure. You need to keep them separate, right? One part low, the other part high. That's it. That's a refrigerator. Think about our lives without a refrigerator. I'll go quickly. How do you define the efficiency of a Carnot engine? Isn't it W by QH? Come on. Second one, work is QH minus QC, which gives you another formula. And then you have a third formula in terms of the temperatures. Hey, what scale should temperature be taken in when you do all these calculations? It should always be in Kelvin. Please be in Kelvin. Now we stop short of what is the COP. Oh, the efficiency of a refrigerator is not called an efficiency at all. Because any number that can go more than 100 cannot be called efficiency. Therefore, it's called coefficient of performance. Coefficient of performance. And the reason is modern refrigerators could have that number like between 7 and 8. So that's like 700%, you see? So you cannot call it efficiency. Symbol is KR. K stands for coefficient of performance. R stands for a refrigerator. Look at the definition of coefficient of performance. How is it? Kind of surprises you because remember what we were saying? What we put out was QH, isn't it? But that's not what's important. What's important is how much you could, how much you could absorb from the cold object, see? So that's why it's QC by work. Now, isn't work QH minus QC, Mason? Isn't work QH minus QC? That's why you have the second formula and then you have a third formula. Isn't that easy to remember? Okay, let's work out a problem quickly. Normally, where does the refrigerator put out the heat? Into the room. So what would TH be? The room temperature, of course. Let's take it as 27 degrees Celsius. Go. TH is 27 degrees Celsius. Now tell me about TC. TC. 0 or less than 0. In reality, would it be 0 inside or less than 0? Come on. Less than 0. Let's take it as negative 10 degrees Celsius. Okay? Find the coefficient of performance. Quick. TH is 27, TC is negative 10. Find the coefficient of performance. You have 30 seconds, Ian, to give me the answer to that. 0.51. 0.51? You're using this formula?
Oh.
Did you change it to Kelvin?
I took the.
No, do this. Use this formula.
7.1.
That sounds right. 7.1. I was just telling you that the coefficient of performance is like 7, 8. Didn't I tell you that? Yeah. Just wanted to prove it. So what is TC? 263 Kelvin. And TH is 300 Kelvin. That's all you have to do. 263 divided by 300 minus 263. That's, yeah, 300 minus 263 down. 263 on top, which gives you 7.1. Sebastian is a genius. My goodness, that's on YouTube. What is a heat pump? Can somebody tell me how you keep your home warm in winter? You see a heat, that's a heat pump. What do you do? What does it do? See, that's what students tend to think. They think, oh, it takes the heat from the outside. Hey, the outside is already very cold. Yeah, there is some heat there, but not much. So how come you say that you take, that's funny. You don't take heat from the outside, which is very cold, and push it into the, no. So what do?
Heat the air in the house.
So how do you heat the air in the house? Either you have electrical heating or you burn gas. So actually in a heat pump, you actually produce heat. You see, that's what I'm trying to say. So you see the difference? In a refrigerator, what do? Did you produce heat in a refrigerator? No. You just took the heat from the cold object and gave it out into the room. But in a heat pump, you're actually producing heat by burning something. That's why I don't like where they compared the refrigerator and the heat pump. They said it's the same thing. It's not. Now, as a result, in a heat pump, the formula for coefficient of performance changes. Watch. Tell me the difference. What did you have for a refrigerator? Come on, what did you have for a refrigerator? You had QC by work, didn't you? For a heat pump, it is what? QH by work. Why? Because didn't we actually put out that heat? We burned something, got the heat, put it out, right? There you go. So the corresponding formulas, you have the other two, because work is always QH minus QC, and then you have, in terms of temperature, you have this. Yeah, there you go. Entropy is actually a measure of disorder of a system. Have you heard that? Entropy is a measure of disorder of a system. The more disordered a system is, the greater its entropy. Think in terms of the molecules of a gas. Think with me. If heat flows into a gas, what happens to the molecular motion? Will it become more random or less random? More random. So what happened to the entropy? Increases. Which means when heat enters the system, the entropy goes up. That's very important for you. If heat leaves the system, its entropy goes down. All right, let's continue on that line. If you continuously remove heat from a substance, you are decreasing its entropy. True or false? True. And if you keep on doing that, what's the lowest temperature that you can reach? Absolute zero. Okay, according to the third law of thermodynamics, the entropy at absolute zero is zero. All molecular motion stopped, right? Everything stopped. So that's the third law of thermodynamics. The entropy, add some words, the entropy of a pure crystalline solid. The entropy of a pure crystalline solid at absolute zero, is the third law of thermodynamics. The entropy of a pure crystalline solid at absolute zero is zero. Got it? Now when it comes to calculations, the only formula that you need for entropy is this. The only formula that you need to know is the change in entropy is equal to dQ by T. Change in entropy is dQ by T. What's dQ?
Change is equal.
Yeah, either the heat given to the system or removed. And T is what?
The temperature
What temperature?
of
This formula seems to imply that the temperature must be a constant, doesn't it?
yeah.
Yes. Because entropy changes only during an isothermal change. Hello, keep listening. What's an adiabatic change? What's an adiabatic change? Where the system is completely closed, insulated. Can heat flow into this? Can heat flow out? So automatically, didn't you make dQ zero? So what's the change in entropy for an adiabatic process? Did you get it? All right, so change in entropy for an adiabatic process is zero. That's important. Change in entropy for an adiabatic process is zero because dQ is zero. So let's work out one problem. First, an easier problem. What is the change in entropy when 1 kilogram of water is frozen to ice? What is the change in entropy when 1 kilogram of water is changed to ice? Go ahead, find it. Formula? Did I give you a formula for change in entropy? Yeah? dQ by T, right? Okay, what is dQ in this case? During a change of phase, what formula do you use to find the quantity of heat? Somebody. Thank you. M times what? Right, latent heat divided by T. Okay, what's the mass here? 1 kilogram. What's the latent heat of ice? It'll be given to you. But does anybody remember? 3.33 times 10 to the 5. And what's the temperature? Well, the minute you say zero, your grade becomes zero. All right, you get that number, that's your answer. Can somebody please put that in your calculator, give me the number? It's that easy. Okay. Go ahead. 1,290? 1219. Please give me the unit, Omar. I know you can. It's Q by T. What's the unit of Q? Quantity of heat. So, very good. That's the unit of entropy. joule per Kelvin. Wait, maybe if it's a printed one, we could already use it. Yeah, do the 10th one, please. 10th problem on this. 10th question. Can you read backwards? You have the mass of aluminum. You have the specific capacity given. And this is placed in 1 kilogram of water. At, what's the 1 kilogram? And the specific heat of water will be given to you again. Joule per kilogram per Kelvin. And the temperature of water is 20 degrees Celsius. And the temperature of aluminum is 30 degrees Celsius, right? What we're doing right now is a very important question for the exam. This is almost surely on the exam, because it's a combination of two chapters. First, can you find the final maximum temperature when you mix them? Go ahead. We've done that, haven't we? When you mix a hot object with a cold object, the hot object loses heat and the cold object gains heat. Haven't we done that? Okay, so it's a two-part problem. What is the formula for heat lost or heat gained in this case? Somebody? MCAT. So heat is going to be lost by the aluminum, so it's going to be 3.8 times 900 times, what's the change in temperature of aluminum? It started from 30 and it goes down to not 20, it goes down to what we're trying to find. We don't know. 20 is the temperature of water, correct? 30 cools down to something, 20 heats up to something. Are you with me? Many students make a mistake of putting the final as 20. It's not. So it's 30 minus T final, which we did not know. That should be equal to, what's the heat gained by water? Help me, come on. What's the mass? 1, and then specific heat is 4185. Be careful on this one. What is the change in temperature of water? TF minus what? 20. TF minus 20. So you calculate TF there from that. Ian, are you calculating? Are you doing anything in this class? Could you just step out, please, for a second? We need to find the change in entropy of aluminum. Will that be positive or negative? Change in entropy of aluminum. Is aluminum losing heat or gaining heat? Losing heat. So that change in entropy will be a negative. But when we come to the change in entropy of water, it's going to be positive. Okay, can you do that? Yes, we can. Let's first do the change in entropy of aluminum. ds of aluminum is the heat that it lost. What was the heat that it lost? Wasn't it 3.8 times 900 times, started from 30, and what was the 24.5? Did you see what I did just now? I used, there's no problem because it's a change, right? Did you all notice the step? Isn't that how much heat it lost? So once you get TF, you plug it back in there and then divide it by, very important, what's the temperature of aluminum? I mean, it started out at 30 and it finished at, and if you have to give a temperature, a single temperature, what would you give? You can give 2, you have to give a number. It should be the average. So that's another place where people make a mistake. And the average has to be in Kelvin. Why? On the top, if you do this in Kelvin or in Celsius, wouldn't you get the same number? Because it's a difference. But in the denominator, do you have a difference in that formula? No, you only have. Are you all listening? I found major mistakes here. So please keep that in Kelvin. Find the average. What is the average of 30 and 24.5? Help me out. 27.25. Add 273 to that, please. 325.25? I'm just simply writing. How much is it? I'm not even watching that. 300.25, yeah. So that's, divide that by 300.25. Do you get a number for that? Time is stressing me out because we need to finish it before. The loss, the change in entropy of water. The change of entropy of water. What do you get? Change in entropy of water. Hey, wouldn't this be the same number? Because the heat lost by copper is exactly the heat gained by the water, right? Wouldn't the numerator be the same? Sure. Or maybe you want to do it that way. Okay, go ahead. You will get the same number in the numerator. You would get 24.5 minus 20. Did you get what I said? Because didn't you first set them equal? Heat lost is equal to heat gain. You don't have to do that calculation again. But you have to take the average. What's the average? 24.5 plus 20 by 2, which is 0.25. Yeah, 22.25. Add 273 to that. 285.25, is it? 95, sorry. 295.25. 295.25 there. And you get a number here. How much?
63.8.
That's where the whole story starts. So you see that the positive is bigger than the negative, and that's always going to be the case. Always. So what's the net change? Net change. Net change is equal to 63.8 minus, which is going to give you some positive number. How much is that? 1 point? Yeah, 2 according to this. So conclusion. We just considered one change, right? You mix two objects and what did we find? We found that the net change in entropy is positive, which means the entropy is it increasing or decreasing? Don't try the creasing game. Is it increasing or decreasing? Increasing. Therefore, when all these processes take place in the universe, the entropy of the universe is increasing continuously. And I want to leave you with another definition of entropy. Entropy is a measure of unavailable energy. You're saying, what is unavailable energy? Hey, energy is useless if you cannot use it to do work, correct? Now, when we walk every day because of friction, isn't a part of the energy getting converted into heat? Come on. Machines work all the time. It's getting converted into heat. Can you ever use that heat energy and put it back into work? The answer is no. No, that's unavailable energy. It's now like being in the ocean with not a drop to drink. So as we progress through life, since the entropy of the universe is continuously increasing, the unavailable energy is increasing. Are you with me? Scientists call this heat death. We're soon coming to a place, the soon may be millions of years, I don't know, but we are going to come to a place where ultimately no engine will ever work. Now tie in that with global warming and it all makes sense. Come on. Although that is a political debate on its own, but still. Let's stay on the heat death part. Did you understand the heat death part? Where the unavailable energy is increasing